Okay, thank you, Cloud Person. So good morning and welcome back. Unlike last semester, the approach I'm going to take this semester is to use the morning session as a class and use the afternoon session or the noon session as the lab. And that affords me the ability to talk about the stuff we're going to do in lab, right? And that sort of works a little bit better than what we did last semester in stochastic computing. Okay? All right. So why don't we get started? Today, the focus is going to be on Arduino basics. And this is going to provide you some information that is going to be useful, getting you familiar with the board and some of the considerations, some of the background behind Arduino that we're going to use during this afternoon session today. And so I'm hoping to get you out maybe 10 minutes early, 15 if we push a little bit, so that you can have a semblance of a lunch break between this session and the back-to-back session, which is at noon. Okay? All right. Well, why don't we get started? But before we do so, some administrative bits. Let me see if that works. Okay. And so the reading, of course, is there. Again, I won't test you on the reading. I just assume you're going to keep up with the reading. I'll always tell you what the reading is and tell you a deadline by which you really should get it done. It's very easy reading from Exploring Arduino, Chapter 1, pages 3 through 21, and Design Thinking, the content, forward, and intro sections, which constitutes pages 4 through 12. Okay. Project number 1, which was out at the start of class on Tuesday, the first class, I should say, more correctly, is due the 25th of January, so this Tuesday at 11:59 and 59 seconds p.m. That's 1 second before midnight. It's electronic on Moodle, and please follow the instructions for the submission. When you do not follow the instructions, you make it much harder for me to get everything graded. I do not have a TA, and so I'm your TA. If it becomes a recurring issue, I will deduct style points for people who are chronically not following the instructions. If you have any questions about it, please reach out, communicate, okay? All right, so any questions about Project 1? Has anyone taken the Myers-Briggs yet? Any surprises? No? Or you kind of knew what it already said? Okay, all right. Now, companies will spend tens of thousands of dollars on this same Myers-Briggs personality typing, because as I said in the first class, it's really important in various industries, particularly those such as consulting types of organizations. Okay, and so I have a couple other points to say, and I'll just say ahead of time, yesterday when I was dropping my daughter off to school, I slipped and fell on the ice and banged myself up pretty good. And so, a little bit bumped and bruised and stuff like that. If you've ever played contact sports like football, after a game, you're really kind of sore and achy and stuff like that. So if you see me grunt and, grimace, it's nothing any of you said. It's just kind of motoring through being banged up a little bit. So that being said, as you'll notice on the Moodle site, I almost said Blackboard, been using Blackboard for 11 years. On the Moodle site, you'll see a link to my meeting room. Please do not join the Zoom session through this link unless directed to do so. As part of our contingency planning for the semester, the administration has asked each faculty member to come up with COVID plans. And so if somebody is sick or having to quarantine, maybe you went away to spring break and you're stuck someplace, because you were tested positive, right? That's what it's intended for. So I got the notification that someone was joining. I won't mention names, it's not important, but please do not join the Zoom session unless directed to do so. I consider it a little bit of a distraction because if you note, I have to attend to the Zoom session and divide my attention span between those who are here and those in the Zoom session. So that's for emergency use only for those specific purposes. Any questions about this? No? All right. And so I am more than happy to chat with you, and I've done that even last semester with all sorts of students about all sorts of things, and some things that have nothing to do with the content material, like resume and career and some things about life in general. I'm more than happy to do that, but I ask you please to schedule those times. When I'm in my office, whether you believe it or not, very often I'm in the middle of working on something, and it helps me to help you best if you schedule those times. Okay? All right. Any questions? No questions? All right. And so we're going to spend a little bit of time on notable constructs in various programming languages that we need for the boards, specifically for the Arduino, a subset of C++ that is called Sketch in the Arduino community, and specifically for the Raspberry Pi, some Python. Now, please note that this is not a Python course, and this is not a programming languages course for C++. Now, that might kind of rub some of you the wrong way, but I don't want to spend the whole semester dealing with the language and syntax of various systems, because that wouldn't mean we'd have time to cover the important aspects of IoT, like distributed systems, networking, programming models, and so forth. And so that being the case, for all of you, this is probably your second or third computer language, and I'll certainly focus on highlighting those notable items that make certain languages different from one another, but I'm not going to spend a lot of time teaching you how to program in C++. That's not the purpose of the course. And really, that's what happens in industry, right? When I was an undergrad, I read something called register transfer language and assembler language for the 8085 processor. Then when I got into industry after graduating, we looked at the 8088 processor, and the assembly for that was different. I learned C over my career, and then I learned C++, and I never learned that in school. And so every 5 years or so, literally, you're going to have to get up to speed on new tools and new languages. And so I'm more than happy to help you succeed, but I can't teach you. We don't have the time in the 15 weeks of the semester to teach this as a programming languages course. And so I've put lots and lots of resources that I've curated on the resources section for the class Moodle site. They're very fantastically done. And how I'd recommend you use these resources is not reading it or watching it from beginning to end in its entirety, but using it as reference. And so in Python and in Java, you've covered stuff like variables and types. You've covered blocks, conditionals. You've covered iteration, while loops, and for loops. You've covered certain structures like arrays and all sorts of stuff, functions, how you take parameters and functions or pass parameters, how you return from a function, and various semantics and libraries. And so one of the things to do is say, okay, well, I know what I want my computation to do. I need iteration. I need a conditional. I know this is a conditional in Python. What is it in Sketch? Right? And it's very similar. And in fact, you've all taken Java, is that right? In data structures, done Java? Well, Java and C++, Java purposefully in its design, Guy Steele at Sun Microsystems Research Lab is now defunct. They made the syntax very similar to C++. And the reason for that historically was because the majority of programmers at the time were C++ programmers. So that was just very clever advertising, so to speak. And so if you've done Java, Sketch will make a lot of sense, but there are some C++ isms that I will cover because Java is an interpreted language, whereas C++ is a compiled language. Java's language is interpreted by this so-called virtual machine. And virtual machines were not pioneered by Sun Microsystems. They were pioneered by IBM in the 70s. And the Java virtual machine, as cast by Sun Microsystems, is really just a more modern incarnation of some of the work done in the 70s by IBM. And I'm happy to talk about that. I worked at Sun Microsystems for a number of years. It was a lot of fun. But that being the case, any questions? No questions? Okay. So when we last left off, we talked about the so-called sense, think, act cycle, and we used that as a motivation to talk about what is an IoT system. And we said we have an embodied, situated agent, and so it has a physical presence, and that physical presence is in the environment. So it's participating in the environment. It's not just casually observing it from afar. And so this embodied agent or embodied system It measures its environment through these devices we call sensors. And we said these sensors convert energy from its native form in the environment into electrical signals. And then it takes these inputs, these measurements of the environment, and updates its understanding of what's happening in the environment, be that populating a data structure or updating some kind of model. And then it runs some computation on that data structure or model, comes up with a solution, and performs some action through these other devices called as actuators. And we said this cycle continues, the sense, think, act cycle. And we said that an IoT system, oh, why did that break? Is nothing more than a robot that has been broken apart and its pieces are scattered around the network. And when you scatter these pieces around the network, because they're no longer part of a system, you need to add some computation to each piece and some networking to each piece. And as we said, IoT is really just a symptom of a bunch of advancements, namely miniaturization, so we can make circuits really, really small, as well as easy networking, so we can network them, as well as low-cost embedded processing, right? Any questions about this? No? Okay. So we also talked about melting pot diversity and salad bowl diversity, and how when you interact with people, sometimes it's good to understand what their personality type is so that you can then model conversation that leads to, or interaction that leads to smoother group dynamics. Okay, any questions? No? No questions, all right. And so let's talk about the substantive material. We're going to begin with the Arduino boards. And so the history of Arduino is pretty interesting. And it's one of those examples where something that began in earnest as a teaching tool kind of took the world by storm. Now, the Arduino is interesting in that it's open source. And you can actually download and find, it's no secret, all of the design files that show you precisely what all the circuits are that comprise the board. And if you chose to, you could actually go ahead, get it manufactured. There are a lot of independent fabs out there that'll do it for you for a cost, and enterprise to sell them yourself. There's nothing special about that. And so from your own searching for the Uno board for the course, you probably noticed there are a lot of boards, some by Arduino organization, some by other manufacturers, right? And so those have enterprise to actually make a living or make a profit, so to speak, from, this is gonna be interesting, make a profit from selling implementations of these clone boards. I'm not sure why it's doing that. All right, I hope my mic is still hot. Check, yeah, it's still hot. And so it was designed specifically to be easy to use, and it was the result of somebody's master's thesis, right? So you can do very impactful work in a relatively short order, just in a fifth-year master's or two-year master's. Question? A clone board? A clone board is a board that some other manufacturer has decided to produce and sell, and it should be ideally compatible with the specification. And so when you buy a computer, for example, you have an Apple Mac, right? You can only buy it from Apple, but the other kind, the so-called PC, is actually a clone of the IBM PC design. And so a clone board is just, I don't want to call it a knockoff because they're actually licensed and authorized to produce their own, okay? All right, and one of the tricky parts, as we alluded to last time with a clone board, well, that compatibility issue, right? Some might decide, hey, we're going to do things a little bit differently, right? And you want to make sure they're compatible with the software library as well as with the signals for the circuits on the board. Any other questions? No? All right. And so what does this Arduino platform consist of? Well, it's the design for the circuit board, okay, but it's also the productivity tools, namely the IDE, integrated development environment, that allows you to write programs in a, something is weird. Hadn't done this last semester. It's the hardware as well as the runtime environment, the libraries, and the software and the IDE for being productive. Now, The Arduino IDE from Arduino.cc, the de facto source, is not the only development environment that you can use. There's something called Platform IO. There are other IDEs by different manufacturers that you can use, but we're going to use the Arduino IDE that's available for free from the Arduino website. And these boards exist in a whole host of form factors that serve various purposes, and we'll touch upon a little bit some of these purposes, but there are also commercially hardened available versions of the Arduino platform. And so if you wanted to produce something that would go airborne and it had to survive in harsh environments, yes, there is an industrial grade hardened version of Arduino boards out there. Okay, all right, any questions? No? All right, so this was the first board. Now, of course, it's the Arduino Uno revision 3. It started out with the revision 1. And back then, they didn't call it the revision 1. They just called it the Arduino Uno. Now, this was what they kind of made their name on. And this particular version of the Arduino is called the Arduino Uno revision 3 SMD. SMD stands for Surface Mounted Device. Now, if I direct your attention to the bottom center right of this board, you'll see this computer chip. And that computer chip is a so-called surface mounted device. And we'll talk a little bit more about what that means. There's another version of the same Uno revision 3, the so-called DIP version. DIP stands for dual inline package. And one of the things you'll notice is there's a difference between the chip here, and that's the main processor, and the chip here. That's the main processor. These two boards functionally are 100% the same. The only difference is in what that main processor is using as technology to attach it to the other circuits that comprise the board. Okay, any questions? No? And so the purposes as to why you would use surface mount versus dip, well, with the dip, you'll notice here, there's a silicon chip, a computer chip, and this silicon chip, and I wish I had another view of it, is plugged into a socket. And so if you accidentally, for whatever reason, because it's going to happen, burned out your main processor, you just get another one for much less than buying an entire board. You pull that one out and you plug in the new one, right? It allows you to replace things should they burn out. Now, I'm going to play a video that talks about the difference between what's called drill through and surface mount. And I forgot to mention this, that if we were to look on the underside of the board, we would see holes filled with what looks like melted metal called solder. And that's how you attach these sockets and some of these components. You drill a hole through the board, you push that connector through, a piece of metal for the conductor sticks out, and then you apply some solder, which is a molten metal alloy. Okay, so let's take a look at this video for a little bit. It's about maybe 3 minutes or so. Now in England, they say SMT, not SMD. Here it's SMD. Large-scale production using blue-hole codes, wave soldering is used. This is where the circuit board moves the solder wave tank, resulting in the application of molten solder. A strong bond is created when running the heat or resulting in the able to withstand harsh temperature and environmental stress or high heat. DHT method is easy to change out testing application that require manual adjustment. Now, let's take a look at the surface mount method. The surface mount method allows for 1,000 tiny electrical components to attach to the copper contact pad, after which the entire assembly is subjected to cold heat. The solder base is
placed on the circuit board and then components are added directly onto the PCB. The whole circuit board is then done, allowing flux paste to liquefy and then solidify all the form of the contact pad and the component. This method of soldering is known as reflow soldering. No critical holes required, doesn't keep components difficult to forward, and can be mounted on both sides of the board. Time for a recap. Through-hole mounting tends to be more costly and time-consuming. Through holes is more reliable and durable for applications that experience movement and high temperatures. Through-hole mounting switches can be placed on both sides of the board in low density. SMT components can be placed up to 10 times faster than THT, therefore it seems more economical. Pasting switches are quickly placed on the board when moving up and conveyor track. SMT switches can be placed on both sides of the PCB in a higher density. Here's a bit of history for you.
Okay.
Technology was standard practice until surface mount technology developed.
Okay, so we'll stop there. You're free to check the URL yourself if you want to watch it in its entirety. And like many things, right, there's an engineering trade-off. Some things are going to be cheaper. Some things are going to be more compact. So if you had a very small footprint device and you wanted to add Arduino circuits to it, you would use surface mount technology because you can pack more things in there. But if you had something that was intended for a ruggedized environment, maybe something that was airborne, high enough in the atmosphere that it was subjected to maybe a lot of vibrations because of air currents and turbulence, as well as extreme temperatures, you might want to use the through-hole technology because it's more mechanically durable. Okay. All right. Any questions? So if you looked at the Arduino board and you saw different types, both being sold as the same thing, they're functionally equivalent. And one of the things you will see in the name is the type of technology used to mount the main processor board. Okay, so this is the Arduino. And if we sort of unpack some of the items on the Arduino, one of the things that you'll see mentioned in the specifications is the main processor. Now, the company Amtel makes the AT Mega, and they'll tell you what the processor is. And it's up to you to look up the specification, Google search it for the processor, and it'll tell you things like how many MIPS of computation it's able to perform, the amount of memory it has, the amount of I/O that it can drive. Now, depending on your application, you're going to choose a processor and a board that is suitable for your purpose. And we'll talk a little bit more about that. So the plain vanilla Uno 3 has the main processor board, the AT Mega 328P. It also has a second processor, and the second processor, the 1602, is purposed with translating or bridging between the USB protocol, it's a bus-based protocol, and the internals of the chip. Because inside this board, things are serial, but when you look at something like USB, it's address-based. Every device that you plug into a USB bus gets a unique number, its address, and then there's a ping that says, hey, I want to send something to this particular address, right? And that works very differently from something that's a serial connection where you're sending a sequence of bits along one wire. And so this chip, the AT Mega 1602, is used to translate between this USB address-based bus protocol and the internals to get data on and off of this board through the USB cable. Okay, any questions about this? No? All right. So we also have a crystal, and crystals are very important to circuit boards. And the crystal typically has a crystal inside of it. And this is a very special type of crystal, typically a piezoelectric crystal. And what this crystal does, when you energize it with voltage, it'll start to vibrate. And it doesn't just vibrate arbitrarily, it vibrates or oscillates at a characteristic rate, so many vibrations per second or cycles per second. And this is used to set the timer for all of the operations on the processor board, because things have to happen at a characteristic rate in order to get any sort of computation to work. That includes I/O, it includes doing arithmetic, it includes doing logic expressions, everything. And so this crystal is what sets the timer. It's like the clock that you use, or almost like a metronome if you play instrumental music. It's what drives what happens on your main board. Then lastly, we have two sets of pins, the I/O or input-output pins. We have along the top, the digital input-output pins, and we have along the bottom, the analog input-output pins. Now, analog in computer speak, you can think of as a real valued voltage or signal. And real valued, of course, up to a max and min. And so with these analog I/O pins, programmatically, you can either send out a voltage or read a voltage. So this is used for all sorts of devices. And let's contrast that with the digital I/O pins. These input or output digital signals. And in computer speak, a digital signal is either true or false, but if you actually measure it, it's either the presence of voltage, plus 5 volts, or the absence of voltage, 0 volts. Now, if you were to take a scope and actually measure it, it's not really 0 volts, it's effectively 0. It's like 0.3, 0.4 volts up to a threshold, but you can think of it as 0 volts is a logic false, and plus 5 volts, plus or minus some delta, is a logical true. And so together with the digital I/O pins, which are programmatic as well, and the analog I/O pins, you're going to interface with various devices, namely your sensors and your actuators. Okay, any questions about this? Questions? Yes. Your crystal, it's somewhere on there. Trust me though, it does have a crystal. Without a crystal, it's not gonna work. Okay. Any other questions? No. Now I talked about the Uno revision 3. I haven't talked about the Wi-Fi 2. So let's get to the Wi-Fi 2. Now, of course, that was the Uno revision 3. And you'll notice here, it has 14 digital I/O pins and it has 6 analog I/O pins. But what do you do if you have an application that requires a lot of input output? For example, what if you have a robot mechanism? If your robot mechanism is what's called a 7 degree of freedom arm, a degree of freedom in robotics, you can think of it as a rotational axis driven by a motor. And so if my arm were robotic, I'd have one motor to make it do this. I'd have another motor to make it do this, another motor to make it rotate that way. So that's 3 motors. I'd have one for my elbow. I'd have one, 2, and rotate for my wrist, another 3, and then the 7th one to make my hand open and close. And that's even if with just a basic gripper, if I had fingers, it'd even be more complex. And so with all of those motors, you're going to need to control each one in a coordinated fashion to get the motions that you need for a complex mechanism like a robot arm. Now, that being the case, of course, for something like the Uno revision 3, you're going to run out of I/O pins. And so there are other so-called form factors or versions or variations of the Arduino. In particular, the Mega Arduino platform has a lot more digital and analog I/O on its bus interface. And so here you'll see the Mega and the Genuino have all sorts of neat names for it, with various differences. It has 54 digital I/O pins and 16 analog I/O pins. And that's a lot more than the plain vanilla Uno revision 3. And so if you had an application, it could be factory automation, it could be a robot, what have you, and you need a lot more I/O than is afforded by the Uno revision 3, you'd use the Mega platform. Now, of course, Mega platform and the Uno platform, there are industrial grade hardened versions. And if you were actually on a factory floor, let's say, industrial application, you were manufacturing something and it was a very hot, dusty environment in a factory, of course, you wouldn't use this version of the Mega. You would use the industrial hardened version of the Mega. And there are lots and lots of vendors that sell variations of these. Okay, any questions? No questions? Make sense? Yeah. And so down here is the Leonardo, and I'm not going to cover every single variation on the board, but the Leonardo adds this USB stuff on board. And when you plug this thing in, it acts like a USB mouse, right? You just plug it in and it participates, shows up as a USB mouse, which is kind of nice for certain applications. If we look here, sometimes you want something much smaller, right, in its form factor. Maybe you're going to put it in a small device and you can't have a huge credit card sized board. This is the Nano. And you'll notice the Nano, this is the underside of the board, it's surface mounted. And you'll see these holes here, these solder beads, that's the drill through, right? The top of the board looks like the following. It has these interface pins, so it's mostly I/O, but the amount of memory and processing on this is very modest. And so it connects with a mini USB connector. And for a sense of size and scale, it's about the size, a little bit shorter than a stick of gum, right? It's very, very small. And these Arduino platforms, you can get one that's button size, really, really tiny. Now, of course, when you go down in form factor, you're now getting more and more modest in the amount of computation and memory that you have. So how you write your application is going to matter depending on the platform. Any questions? No? All right. And so if you were to do this, quote unquote, for real in the wild, one of the first things you have to look at is your application requirements. Where is it going to operate? What are the characteristics of the environment in which it'll operate? Because that's going to shape your choice of which board you're going to use. Okay? All right. And so this is the board we're using, the Arduino Uno Wi-Fi. And the reason why we're using it is because it's very well tuned to IoT types of applications. And so I've written down a couple of features. It's used to build sensor networks. Now, when I was in grad school, they didn't call it IoT, they called it sensor networks, right? And smart rooms and stuff like that. So it's interesting, history repeats itself with different nomenclature. But that being the case, it has all sorts of communication ability. It's called the Uno Wi-Fi because the Wi-Fi chipset is built in the device itself. And if you're curious, the antenna is in here. It's just a conductor. You put your RF signal energy on that conductor, and it propagates out into the environment, into the airways. It also has Bluetooth. So you can, BLE stands for Bluetooth Low Energy. And so there are APIs for doing Bluetooth communication with Bluetooth-enabled devices. It also allows you, of course, to connect to a Wi-Fi network, but there's a crypto chip in it, so you can do secure communications, right? It has an IMU, inertial measurement unit, so you can move the thing and you can measure those velocity and acceleration vectors. So maybe you have an application, if you look at your cell phone like an iPhone, you take it out and you do this, all of a sudden the screen wakes up. That's because of your IMUs, right? It measures motion vectors and velocity vectors and accelerations. Okay. It also has an integrated TCP/IP stack. We'll talk a little bit about networking, but we're not going to give the same treatment that a computer networking course has. TCP/IP stands for Transmission Control Protocol, Internet Protocol. TCP part talks about the reliable delivery of messages between two communicating endpoints, and IP talks about the global identity and storing and forwarding of chunks of data called packets throughout the network infrastructure. And we'll talk a little bit about that because it's important to understand something about networks in order to write good network applications. Okay, any questions about this? No? In addition, wait, there's more, like those infomercials. It also has the ability to communicate with RFID tags, right? Which is nice. So it does everything. It has a bunch of analog I/O, digital I/O. It has a USB connector, which we can see up here, and it has a power connector. Now, certainly, if you deploy such a thing, you have to give it a power source, and you give it its power source through the barrel power connector and not the USB. But you can still drive the board at the desktop power-wise from the USB connector, unless you're really pushing the board hard and your I/O devices, such as motors, are very power hungry. USB might not support the amount of voltage that your board is going to need. Okay? And any questions about this? So why did I choose the Uno Wi-Fi and not the Uno 3? Well, for one, the Wi-Fi has Wi-Fi built in, but it's a little bit more involved than that. So we're going to talk about this idea of stacks. Now, this is a schematic of the Uno Wi-Fi in particular, not the Uno revision 3. And so numbered here in this legend are various parts of this board. Now here we have the main brain of the system, right? So that's for memory, for instruction fetch, instruction decode, instruction execution, right? As well as driving the I/O. That's the main processor. Of course, the USB connector we talked about, the power port we talked about. Here, number 4 up here, right there, we have flash. ISP stands for in-circuit serial programming. And so that's where when you try to upload a program to the Uno, it uses that chipset to effectively take the byte code, the ones and zeros for your translated program, and put it into the firmware, that electrically programmable part of your computer, of the board. And so we also have the Wi-Fi module here, which I talked about before, and it's the Wi-Fi Nina chipset. Here's the antenna right here. And then we also have the IMU, number 7, the tiny little chip. Where is it? Right here. That's the inertial measurement unit. And then we have some LEDs, of course, the analog I/O down here, the digital I/O up here, and it has some voltage shaping called a voltage regulator. That's for giving you stable power. Now, it's really important for digital systems to have stable power, because if you were to measure even direct current going into such a board, well, it's going to flicker a little bit. And one of the issues you have with digital circuits is that you need stable current, because if that current drops a little bit below what it should be, the board's just going to shut off. And so you need something called a power regulator that takes the actual voltage and makes it much more smooth signal. And we're going to talk a little bit more about that in future module. Okay, any questions about this? Yes. Oh, ICSP, in-circuit serial programmer. That's this header. And it's used for something called serial peripheral interface, or SPI, which we won't talk about right now, maybe a little bit later, depending on time. But it's essentially used to send programs dynamically into another circuit. It could be for circuits on this board or circuits on another board. It's called in-circuit serial programming. Okay. Any other questions? No? All right. And so, why is this blocking? And so if we look at the Arduino, this is the Uno 3 again. We call the analog and digital I/O pins the so-called signal pins, because that's what it uses to communicate with devices. You can think of these devices almost like the peripherals on your computer. You have the main processor board, you have your storage, your disk, you have your RAM for temporary storage, but you also have things like mouse, printer, keyboard, monitor, and things like that. So each one of these quote unquote peripherals, in the case of the board, these are devices that you'll program, your sensors and your actuators, and you can think of them as the signal lines. It's how you talk to other things from the perspective of the board and how other things talk to you. And so when we look at these signal pins in the Arduino ecosystem, you can use so-called daughter boards to expand the capabilities of the base level board. And so why would you do that? Well, because sometimes for some applications, it's much cleaner to have it implemented in silicon as a set of chips that do it, rather than doing it completely in software. Because when you do things in silicon, it runs at full chip speed rather than interpreting software, right? So let's take a look at one such shield, or daughter board as it's called. This is the motor shield. Now, absolutely, you can control a motor directly from the board, but for certain types of motor control, and especially if you have a lot of motors, like the robot arm example that I alluded to earlier, you want to do it in silicon. And so here we have the motor shield, and you'll notice there's some pins that extend out along the front and the back edge. Now, these pins go in these sockets for the analog and digital I/O pins on the Uno board, and they mate electrically, making a connection when you plug that board in. And so this is the plugging in of the motor shield onto the Uno revision 3. And this is what it looks like when you've plugged it in. And so together, these two will implement motor control in a more sophisticated way that you would have had to do in software. And it also has, if you notice here, these tie points, electrical tie points, they can accept much higher voltages and currents than the base level Arduino board can. Okay, any questions about this? And so one of the things we'll talk about is PWM, or pulse width modulation. But when you do that, well, of course, you have to turn on and turn off your signal on the board yourself in software. But with the motor control board, you just say, give me this duty cycle in PWM, and we'll talk about what that means later in a future module, and it will do it for you, right? So something that you'd have to implement in software, this motor controller board does for you just by giving it a simpler command, okay? So it's almost like a library API implemented in silicon. All right, any questions about this? No questions? No, makes sense? Yeah, all right. And so this is this Wi-Fi shield. And if you had an Arduino Uno revision 3, not the Arduino Wi-Fi that we're using for this class, in order for it to do Wi-Fi communications, you'd need to buy this shield and plug it into the Uno 3. And the Uno 3, along with this Wi-Fi shield, gives you most, but not all, of the features of the Arduino Uno Wi-Fi revision 2, right? This adds Wi-Fi, some Bluetooth, but it doesn't have the IMU. It doesn't have the, well, the new ones might have cryptography, but it doesn't give you all of the features. Now, you might ask, well, why didn't we do that? Why are we using the Uno Wi-Fi revision 2? Well, because you can get really, really tricky conflicts whenever you add shields again and again and again, one atop the other. And so let me explain what I mean by that. Here's another shield called the Electronic Health Sensor Shield, or e-health sensor shield. Now, this particular shield drives certain medical devices. So you can measure airflow, you can measure electrocardiogram. If you have a glucometer, you can track the glucose measurements. And this is for a digital health application. Now, this board adds the control logic for speaking appropriately with these various devices that you can hang off of it. And it's quite a few devices that it can drive at the same time. And that's why someone chose to implement this in silicon as a shield. Now, I hope this isn't an issue all semester with this thing. I don't know why this doesn't, okay. Now, a couple of years ago, I had a research project where we built a peer-to-peer pluggable framework for medical monitoring. And the reason for that was so that you can place your computation arbitrarily across the network. You'd have some more analytical components in a blade and a data center, and others were backed by these devices. And so in this experiment, we used the e-health sensor shield, and we were looking at pulse and oxygen saturation, the pulse oximeter, SpO2, electrocardiogram. And for the electrocardiogram, when you have biosignals, such as your heart rate, you have ions circulating in your body. In particular, your neurons use sodium and potassium to send electrical impulses for things like your heart. Granted, your heart signal is something that's autonomic. You don't have to think, okay, beat, 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 right? It happens automatically. So you place a sensor over your heart and another sensor someplace near your heart. And that difference in the flow of ions has a potential or voltage that's measured as your heart signal. And so there's that characteristic heart signal that kind of goes across, you see on all the medical shows. And so we have ECG, we have skin temperature, which goes under your armpit, airflow. So a couple of things. And so this is what the board looks like. And as you can see in this stack, we had 4 things. We had the Uno revision 3, the health sensor shield, the first version. Now they're on version 2. We had the Zigbee shield, and the Zigbee shield was for body area networks. IEEE 802.15.4 protocol, which is for low power near area wireless networking for sensor networks. And then on top of the Zigbee shield, you have a translator board, the Wi-Fi module, which then takes that ability to talk Zigbee protocol and turns it to 802.11, which is your Wi-Fi. And so this stack of course, is 4 daughter boards high, the base board plus 3 add-on boards. And the more shields that you add, the more conflicts you're going to get, because some of these boards, these shields, use signal pins in ways that you might not expect. And so what do? You have to study each board, and they say, okay, which pins is it using? And then if you want to use other pins for other stuff, you really have to be careful to make sure that no other board is using those signal pins, okay? And so in this, we implemented an HTTP 1.0 compliant web server as a finite state machine. We did that because we wanted it to be really, really small, because our goal was to get to a button-sized Arduino platform to wear these sensors, to kind of build what looks like maybe you're too young to remember Sony Walkman, but a Sony Walkman that you put on your hip, a little portable device that you then hang these things off of so you can walk around in a room quite easily. Okay, any questions? And so the reason we chose the Arduino Uno Wi-Fi revision 2 is because it gets really, really complicated as you add more shields. And so you'd add a Wi-Fi shield to the Uno 3, and then if you wanted to do Bluetooth, have a Bluetooth shield, and then if you wanted to do something else, you add another shield for that, and then you're getting all these conflicts, and it happens very, very fast. Okay, any questions about this? No, does that make sense? And so when you're designing things, absolutely, you can add all sorts of features. You name it, there's a shield for it. You have to be very careful that you're not going to introduce signal conflicts, because it happens very fast. After 2 or 3 shields, you're going to get tons of conflicts. And so anything that you can think of, there's a shield for that. Because it's open source hardware, so many people worldwide have contributed extensions in hardware that enable your Arduino platform to do just about anything you can imagine. And so there's the motor shield that I talked about, the health sensor shield. There's a GSM shield. Suppose you had an application in agricultural monitoring. Well, you're not going to run cables, and Wi-Fi doesn't stretch across 100 acres, right? It's only 500 feet in the ideal. Well, you might want to use the cellular network in order to pipe your telemetry back and forth. And so there's a GSM shield that can send SMS messages, make phone calls. It can also do telemetry over the wide area over the cell phone network. Okay. And there are all sorts of things. Controller area network for doing things like automotive electronics, a relay shield for switching very high currents. There's a shield that will do that. It's effectively a programmable switch. And there's data logging. There's a GPS shield that will talk to the satellites and give you GPS coordinates. There's an accelerometer that can give you very sophisticated motion measurements. A radar shield, actually doing RF radar, USB shield, you name it, they have it, right? It's limitless. Anything you can think of, somebody has developed a shield for that. Okay, any questions about this? No? So I won't repeat this slide since I talked about it in the first class. This is the Uno Wi-Fi revision 2. And we use this because I want to keep you away from potential conflicts on the signal pins that might be introduced if you choose to extend it in various ways. Okay? All right. Any questions? No questions? No? All right. And so one of the things that's really, really important to become familiar with is electrostatic discharge, or ESD. You've ever walked someplace and you shake someone's hand or touch the doorknob, zap, you get a little shock of electricity, right? Nothing major, nothing painful, nothing detrimental, but to a chip, that's death, right? And so this is a computer chip. And if you didn't know who this is Mark Dean, Inventors Hall of Fame, IBM Fellow. He holds many of the patents to the IBM PC architecture. And he led the team that did the first high-speed gigahertz processor. Now, back in the day, processors weren't gigahertz. That was a big development, and he led the team to do that. But nonetheless, holding in his hands, Dr. Dean has what's called a silicon wafer. Now, this wafer, if you look at it closely, you see lots of little squares in it. Each one of those squares is a computer chip. specifically a processor. And if you blow it up, this processor will look something like this, and it does have that shiny color. And each one of those regions in this processor performs some function. And so a core is nothing more than a full processor, a multi-processor system. And we have memory, we have I/O, we have cache, and all that good stuff, which will rely on you having taken computer architecture, or was it 160 beforehand. And so this chip is put in something called a pad frame, and conductors, usually gold wire, is used to connect the signal lines and data lines for these chips to the printed circuit board. Why do they use gold? Because gold is the best conductor, but it's quite expensive. And because it's so expensive, they only use it where it counts. Many satellite circuits use gold because it's a royal pain. Well, you can't to go and fix a satellite if something's broken, right? So they use that conductor gold in many cases for satellites. And so a cap is put on top of this bonded chip in the pad frame. And this is what it looks like for real. And this bonding with the gold wire is done usually with a robot, right? Because they can make those precise movements to make those signal leads. If it's done by a person, usually you're using some mechanism, driving it with a joystick under a microscope, right? It's really hard to do because it's very, very small. Any questions about this? And so the reason why I'm talking about this is if we kind of zoom in under a microscope to some of the circuits in the chip, static electricity to a chip acts like lightning, right? And so in this example, we've circled a region on the chip, and if we zoom in, you'll see it's sort of zapped away, burned away part of the circuit. And so when you interact with electronics, you really want to be careful of something called electrostatic discharge, right? Or static electricity. And so what you do then is before you interact with a circuit, you want to ground yourself, right? You want to find something typically metallic that is connected to ground, like your computer has a voltage and it's connected to ground. So maybe you touch part of the metal on your computer to make sure that you haven't built up static charge, right? Because you will and can kill a chip by zapping it with static electricity, and you never intended to do so. Okay? All right, any questions? No? And so what happens in practice, if you work a lot with electronics, there's something called an ESD bracelet. And this bracelet straps onto your wrist typically, and it has a little metal that connects to your wrist and has a wire that leads from that. And you clip this thing onto something that's grounded, and that keeps you grounded throughout the course of what you're working on. So if you do a lot of electronics work, you might want to get an ESD bracelet. If you're just doing here and there, just keep in mind, burn into your muscle memory, that it's important to ground yourself before you pick up something that has computer chips on it. Okay? All right, any questions about that? And if you could kindly put your mask back on. Thank you. Any questions about that? No? No questions. Now, you might not believe it, but the first time it happens, you're like, oh, okay. Yeah, ESD is a real thing. All right, so let's take a look a little bit. And we're here till, what, 11:40? 10, 25. Yeah, 11:40. Let's take a little bit, look a little bit at compiling and libraries. Now, this is the de facto source for all of the software pieces, including the IDE and language for Sketch language on the Arduino, and Sketch is a subset of C++. Now there you'll see the IDE, and they have two different versions. One is what I'll call the platform version, which installs on your machine, and the other is a web version. I would strongly recommend the platform version because the web version depends on what's happening on the cloud server and also what's happening with the network. Moreover, the practice I have, maybe it's helpful to you, is I keep all of my code in a web accessible folder. And then, for example, when I'm here, I run the IDE and I point it at my Dropbox folder where I have my code. So wherever I go, I have my code with me. So I prefer the platform version. You're free to use whatever version you want, but platform version seems to work a little bit better, I found in practice. And so one of the things you're going to do in lab this afternoon is you're going to install the IDE platform, and then you're going to choose where you're going to put all of your projects. You're going to ground yourself, and you're going to then plug in your USB cable to your Arduino. Then you're going to verify that your drivers on your system can actually see the USB device for the Arduino Wi-Fi. Is your system seeing it? Then you're going to select the appropriate port. We'll talk a little bit about that in the lab for your Wi-Fi, because you have to identify where the machine sees and the IDE sees your board in order to interact with it. Then you're going to install additional software because the default IDE doesn't have the right software on it to drive your board. And then you're going to make sure you have the Wi-Fi NINA library. And we're going to use this library to get your so-called MAC or media access control address. Now, one of the things that's sort of logistic-wise for this class that we have to deal with is that if you're running it on Wi-Fi, which is what we're going to do, we're on the Wi-Fi network for Clark. And so in order to run on the Wi-Fi network for Clark, and I've already contacted ITS about this, is you're going to have to register your MAC address on a website so you can get a static IP address. And that's my goal, so that you can log into your Arduino and use it to do things using a web browser. Okay? All right. Any questions? No. So that's what lies ahead at noon session. This is what the IDE looks like when you first start up and create a new program. The basic program has 2 entry points. Now, this is the sketch language, C++. It's block structured like Python, but instead of using indentation to define your blocks of behavior for your program, you have the open and close curly brace. So it's exactly like Java in that regard. This sketch, or C++, is a so-called strongly typed language, and it's compiled. So you have to define the types for all of your variables. In Python, it's a dynamic type. It's late binding language, meaning through context, the interpreter figures out what type each variable is. Okay? All right. When you run your program, you'll notice there's no main routine here, right? On the Arduino, you have 2 functions that are the entry points for your program. One is called the setup function, and the setup function does not take any parameters, so that's open and close paren with no parameters in a parameter list. And you'll notice here void, that means it does not return anything. It's a void type. Setup is called whenever you turn on your board or you hit the reset button. It's a one-time thing. It calls a setup, and typically in your setup routine, you're initializing things. What sort of things do you initialize? Well, you're setting up whether, for example, your digital I/O port that you're using is going to be used to output digital signal or read or input digital signal. If you're doing Wi-Fi, your setup routine is used to connect to the network in question. Now, once your setup routine returns, you typically have all your configuration set up and configured. Then it calls this loop function. Now, loop does not take any parameters, void parameterless. So you see open and close paren with no comma separated list, and it does not return anything. And this loop, exactly as the name might imply, it calls it again and again and again and again and again. So once loop terminates, it's called again. Once it terminates, it's called again. Once it terminates or exits, it's called again. And that's where you implement all the behavior for your system. And for that reason, that's why something like a finite state machine is an excellent model for how you implement your programs that run on the Arduino, okay? Because you're calling this timer-based loop, 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 loop continuously until you turn off the power or you reset. But once you turn off the power, if you energize power again, it'll call setup once and then loop repeatedly over time. Okay, any questions about this? Does that make sense? Yeah. All right. And so language, C++, as I said, is strongly typed. And you notice for each variable name, it has the data type. In this case, int or integer, which is signed 32-bit, or depending on the platform, the word size. And then here you have character, which is a single ASCII character, and bool is a Boolean type. Now, you can initialize your variables, and it's really important to initialize them. Unlike Java, it does not default initializations. So if you do not initialize your variables to some known value, it's going to assume whatever value happened to be in memory when it carves out that space in memory. So it's really, really important in this type of application to make sure you're explicit about initializing your variable values and not rely on what happens to be in memory. Okay, it's block structured, which I said before. So you delimit a block or a sequence of instructions that implement some behavior. You explicitly delimit a block with an open curly brace and a closed curly brace. Now, the style I learned, you don't have to use that style, but here's my open curly brace in line with the block. And then here's my closed curly brace. And if you look at it, you can kind of draw a square or a block around that particular unit of behavior. This particular block is a function. And here I've had a single parameter, but you can have a comma separated list of parameters. Each parameter, you have to specify the type as well as the variable name for that parameter. You can also define local variables inside of functions. So here's a local variable. This particular one is a Boolean type, and it's going to get the result of calling a function. Okay. All right. Any questions about this? So it's a lot like Java. In fact, Java is purposefully, as I said before, a lot like C++. All right. And so every statement, if you are more comfortable with Python, every statement in C++ or in Sketch is delimited by a semicolon. And so the fact that I have things on separate lines is really just for human consumption because it looks nicer. But there's nothing that says you can't have one statement, semicolon, followed by another statement on the same line, right? That's perfectly legal C++. But if you want it to be more easily readable, put some space, put some things in there, and put some things on separate lines so it's easier for human consumption. Okay? All right. And so C++ and therefore Sketch is a compiled language. Compiled language means that it's translated from source code, which is just a text file, into bytecode, which is the sequence of zeros and ones, the machine code that's understood by the platform. And so at a naive level, you take your program written in Sketch, you run it through the Arduino compiler, it translates it to Amtel bytecode because it's the Amtel processor that runs the Arduino board. And then you perform staging, and that's the uploading of your bytecode to the processor board. And that happens through the USB AB cable. And so this is very simplistic. And what really happens is there's a second pass for this compiler. This compilation or translation happens in two passes. The first one is called pre-processing, and the second one is the actual translation, which is the compilation. And so when you do pre-processing, there are special commands called preprocessor directives. And two of the major ones that you'll see all over the place is number sign include space, and then in angle brackets, you'll see some name with an extension. And what that does is it says, all right, well, before you actually do the translation, I want you to go find this file on the disk, load it into memory, and paste it where that number sign include command is. And so the reason why that's done is to make your code look better. Because if you included all the stuff from that spi.h file, it would be a lot more messy, and it's not as modular. And so typically that's used to add to your program all the definitions you need for particular types of libraries, okay? And so that's nothing more than effectively load, copy, and paste. And the other type of preprocessor command that you'd be using is number sign define. Now with this number sign define, you see number sign define, space, some string, space, and some other value. It could be a value, it could be another string. And what number sign define is, sometimes that's called, excuse me, a preprocessor macro. That's going to cause a replacement to happen. And so everywhere you see, in this case, num iter, and my style is to make it in all caps. The reason why I make it in all caps is so that you say, aha, there's something special about this. This is something that someone else has added through this preprocessor macro construct. And so everywhere you see num iter for num iterations, it's going to replace that with that other piece of text, 10. And so here in a loop, I have a while loop. While count is less than num iter, count plus plus. Well, that's a lot easier to read, makes your program more readable than just saying while count is less than 10, right? And so count less than 10 is the same as saying count less than num iter, because what happens when the preprocessor runs, it goes ahead and replaces num iter with 10. And that's a string replacement. Question? Static is something like in Java static. Static in Java means that it's a so-called class variable and it does not live in the object instance when the runtime instantiates it. And so it's static is a scoping thing, almost, but this preprocessor, the number sign defined, once the preprocessing happened, it doesn't exist. So it's almost like you did a find and replace in your text editor, right? And so it doesn't exist. But with Java and statics, and you have statics in C++ too, and globals, but that's a scoping thing, not a preprocessor thing, because this doesn't really exist. It just makes it look nice for us. But once you get to the and that's a great question. Thank you for asking that. Once you get to this stage, this number sign defined doesn't exist. It's literally doing a search and replace for you, okay? And there are other things you can do with preprocessing that we won't talk about because this isn't C++. It's Sketch, which is a subset of C++. Okay. Any other questions? No? All right. So once the preprocessor has written, has run, the second pass happens, which is the translation or compilation, and then you get your machine code or byte code, and then that staging happens. But you know what? We're not done yet. Wait, there's more. Now, when you use things like the Wi-Fi Nina library, well, you didn't write that, right? Someone else wrote it. So there's byte code floating around that implements all of the functions for those libraries that you're going to use, okay? Well, that's where the linking comes in. You have code that you've written through this top pass. You have the preprocessing, you have the compilation, and that produces byte code. But that's byte code for the things you have written. That's not byte code or ones and zeros for the machine understandable translation of the system libraries. And so one of the things you're going to load is the system library, and it's the job of a piece of software called the linker to take the byte code for the system library, take the byte code from what you've written, and glue them together, literally, right? Now that glued together system library bytecode with your bytecode, that's your program image, as it's called. And that's what gets loaded when you do the staging. Because you need that implementation, not for just the logic that you've implemented, you also need the implementation for the libraries. And then you take that image and you stage it, upload it to your board. Okay. Any questions? Now, of course, all of this happens for you in the IDE, but my reason for talking about it is because if you forgot to include or load the library you need, it's going to give you a weird error message, such and such undefined. And you're like, oh, undefined? What are you talking about? Ah, I forgot to get the system library for those libraries I'm using. So you need your program, but you also need the binaries, the bytecode for the libraries that you're going to use in your program. Okay? And any questions about this? Make sense? Yeah? All right. So these are some library calls, not all of them, but things that we're going to use this Friday as well as next week Friday. And I won't go through and explain each one. I'll bring these slides back up this afternoon. And these are some Wi-Fi calls. And so, Wi-Fi.begin starts the Wi-Fi subsystem runtime, and then MAC address is going to return the MAC address. We won't be connecting to the network because you can't connect until you register your MAC address and do some other things that I'm going to have to find out from ITS. It's kind of weird here. We don't have a research network. Well, that won't happen for another year or two, but nonetheless, the connection of these boards to the Wi-Fi network is going to take a little bit of doing in how to make it programmatic because you have to do this registration ahead of time. And so that's some of the logistic that will work out. But for today, this afternoon, you'll be using the library, getting comfortable with the IDE environment, doing the Blink demo, and just acquainting yourself with some of the tools. Okay? All right, any questions? No? All right. So with that, that's all I had for now. I will see you all at 12 noon. It's only 20 something minutes, but nonetheless, a little bit of a break. So I'll see you then.